Hello everyone, we would like to introduce our work, MetaH2, a meta-surface-based HDR hyperspectral camera. We are living in a world where cameras play an important role in a wide range of scientific and industrial applications that study the geometric and radiometric characteristics of our surroundings. As two representatives, HDR imaging can get full brightness profiles, and hyperspectral imaging helps understand the detailed material composition. These capabilities are essential in diverse applications such as surveillance, food quality inspection, and beyond. In order to obtain such auxiliary information beyond photographic use, traditional methods typically rely on sequential measurements and their different optical configurations. For example, HDR imaging requires capturing a set of images at different exposure times followed by image fusion. Hyperspectral imaging often involves spatial or spectral scanning to acquire data across multiple wavelengths. However, since these methods only measure subsets of the desired information at a specific time, they face significant challenges when dealing with dynamic scenes. As a result, they are not well suited for real-time or snapshot-based applications. Therefore, our project is motivated by the need of enabling simultaneous high dynamic range and hyperspectral imaging. Past efforts on snapshot HDR imaging have mostly focused on sensor-level innovations. Approaches such as pixel-wise exposure modulation and the development of specialized photosensors have enabled direct encoding of brightness variations. But they suffer from varied motion blur or great hardware complexity. More recently, meta-optics-based HDR imaging has emerged, offering improved dynamic range with reduced reliance on complex post-processing. But these works only report single wavelength operation, hindering their use in real-world scenarios. Therefore, there are always trade-offs between motion blur, hardware complexity, and operational bandwidth with current methods. As for the snapshot hyperspectral imaging, there are a bunch of techniques that encode the spectral information into the image, either using compressed sensing, filter array, or data-driven PSF engineering. But most of them only report effective imaging performance within a constrained dynamic range. To address the limitations and find the potential of combining hyperspectral imaging with exposure bracketing, we introduce a novel meta-surface-based imaging modality capable of capturing both types of information in a single shot. In our system, incident light from a scene is first focused by a refractive achromatic lens, then modulated by a meta-surface that splits the wavefront into 9 distinct propagation directions, each carrying a different fraction of the incident energy. As a result, 9 sub-images, each uniquely exposed and spectrally dispersed, are formed on the photosensor. These measurements jointly encode spectral and radiometric information and are used as input to a deep neural network for the reconstruction. The core of our optical design lies in the beam-splitting meta-surface, modeled as a two-dimensional array of uniform nanocells arranged on a regular grid. Its overall modulation can be discretized into the geometry of the nanostructure inside each cell. Specifically, we select nanocylinder as the basic building block since it helps the phase delay be solely determined by the radius and there is no need to particularly consider the polarization. After running a full-wave simulation, we obtain a library that stores the phase delay of a cell under each radius and wavelength. For every intended focal point on the sensor, we analytically compute the required deflection angle, which corresponds to a desired linear phase profile across the meta-surface. This phase modulation defines the wavefront shaping the metasurface must achieve. Finally, we select the radius of the nanostructure for each nanocell that best approximates this analytical phase. To analyze the system's spectral behavior, we derive its point square function using a wave optics formulation that accounts for the modulation from each optical component and free space propagation. At the design wavelengths, the system forms a focal spot at the targeted off-axis location. At off-design wavelengths, however, the optical modulation of the metasurface deviates. We approximate this behavior using Fourier series expansion of the optical modulation, since the implementation of linear phase corresponds to a periodic shape profile. This deviation will generate some DC component which corresponds to an on-axis focal spot. Another dominant term remains the designed spatial frequency, which forms a spatially shifted off-axis focal spot compared to the designed wavelength. Consequently, our point square function remains consistent in form across wavelengths, with only a wavelength-dependent displacement. This property enables our system to encode spectral information as spatial shifts in the image domain. To simultaneously control the relative exposure of each subimage, we implement a random interleaving strategy to multiplex multiple metasurfaces into a single device. Each nanocell is randomly assigned to one of the 9 deflection directions according to a predefined probability distribution. These probabilities determine the energy allocation to each subimage, effectively controlling its exposure level. This approach allows for both exposure bracketing and spectral encoding to be achieved in a compact and passive optical system. We visualize the point square functions to illustrate the underlying mechanism. The observed PSFs shift in position across wavelengths while maintaining their shape, confirming the validity of our Fourier-based approximation and the system's capability to jointly encode both spectral and radiometric variation within a single optical shot. We study how the proposed optical modality compares with previous snapshot hyperspectral imaging hardware in simulation. We compare our method with other 3 snapshot hyperspectral imaging methods on synthetic data. We reconstruct the hyperspectral data cube from the synthesized measurement of each method using 4 post-processing algorithms and compare the accuracy. From this figure, we know that MetaH2 traces the system's field of view for more subimages, resulting in the highest reconstruction accuracy universally under different metrics and on benchmarked datasets. We also assemble a working prototype for MetaH2, where we condense the combination of beam-splitting metasurface and the reflective lens into a single multi-focusing metasurface that has a small numerical aperture. This figure shows the HDR and hyperspectral reconstruction of sample scenes measured in a lab environment. The objects we image contain reflective areas that require HDR measurement to capture their complete intensity profiles. The prototype demonstrates measuring 60 dB dynamic range and a 10 nanometer spectral resolution using a monochrome photosensor. In summary, we present a novel metasurface imaging modality that combines a deflective metasurface with refractive focusing to simultaneously encode both brightness and spectral information in a single shot. We compare the hyperspectral reconstruction accuracy of our method with other snapshot solutions, and show that it achieves higher accuracy at the cost of reduced field of view. Finally, we validate our system through a working prototype capable of joint HDR and hyperspectral imaging in a controlled lab setting. If you are interested in our work, please scan the QR code for details.